Hello everyone. Lesson 4 in Kinetics and Equilibrium. For those of us who missed class or need a review before the test, I've recorded this for you. So our learning targets in Lesson 4, we're going to talk about potential energy diagrams, which are diagrams. I mean, they're graphs, and you need to learn how to read and interpret them so that we can find important quantities and show how they change, like the heat of the reaction, the effect of adding a catalyst, and all that kind of stuff. So potential energy diagrams show reaction progress and changes in heat. For an exothermic reaction, a potential energy diagram is going to look exactly like this. And so we would need to see what a endothermic reaction one looks like. Well, it's the exact mirrored image of it. Okay, so reminder, exothermic reaction, endothermic reaction. Right, so let's see what we got here. The important parts of those diagrams we're going to have to learn how to label. So for forward reactions, you got to read the reaction from left to right, reactants to products. That's simple. Okay, reactants are on the left, products are on the right, just like all chemical reactants. Reverse reaction, you got to read the diagram from right to left. So if this reaction is going to be run in reverse, you read from right to left. Pretty straightforward. The activated complex always occurs at the peak of the diagram. So if you want to think about those diagrams as roller coasters, the highest point on the roller coaster is the activated complex. The activation energy is the amount of energy required to reach this peak of the diagram, no matter which direction you're heading in. If you're heading from left to right, you got to go up a hill to get to the peak. If you're heading from right to left, you got to go up the hill to get to the peak. The bigger the hill, the more activation energy is required. That's all there is to it. Catalysts are important parts of potential energy diagrams because they will provide a way to lower the height of the peak of that roller coaster. This is really a roller coaster we're talking about. It would basically be a way to ruin the roller coaster experience, but this isn't actually a roller coaster. We're talking about the reaction progress of a chemical reaction. So if you decrease the height of the peak, you're decreasing the barrier for the reaction to occur. So if you have less energy required for the reaction to occur because you've added a catalyst, the reaction will go faster and at lower amount of energy, which may be something that you want to do. The overall heat of a reaction is delta H, it's the enthalpy, and you find the heat of the reaction by subtracting the heat of the products, which is listed for you in the graph on the y-axis, from the heat of the reactants, which is listed for you in that graph on the y-axis again. You trace the levels over the little dotted lines, and you can see the heat that is involved. If delta H is a positive number, the reaction is an endothermic one, because delta H being positive means that reaction absorbed heat. The products have more heat than the reactants did, and therefore that heat came from somewhere. It has soaked it up from the environment. Call that endothermic. If the delta H value is negative, the reaction is exothermic, meaning the products had less heat than the reactants did before. So the heat must have gotten released and it was overall exited the system. Exothermic, negative value for delta H. Okay? So labeling the important parts of the diagram. First, draw yourself up a diagram and label a y-axis potential energy. And we like to put nice even increments on there. So I'm going to do a nice simple one for you. Then you've got to draw yourself the roller coaster. Okay, the roller coaster in this particular one, we're drawing an endothermic diagram. So it starts out at low, a very big hill for activation energy, and then a slow gradual drop down to the bottom. The potential energy of the reactants is there listed on the y-axis, where on the left-hand side we have started. That's where reactants are, left. Now the potential energy of the products is going to be on the right-hand side, or the higher hand side of this particular endothermic diagram. So you can read these values off the y-axis. Now, the difference there is the heat of the reaction. The overall change is shown to you between the gap in those two dotted lines. That star at the top is the activated complex. And that is how much energy it takes to activate the complex. When you calculate the difference between the peak and the heat of the reactants. That's how much energy you got to put in just to get this thing to start going. So we call that the forward activation energy because we're traveling from the left to the right, forward reaction. If you were to label up this tiny little gap here, that would be the activation energy for the reverse reaction. If we were running this reaction backwards, it takes less energy to get to the top of the activated complex. Now, I think there's one more thing we need to put in here. Oh, exothermic. So it's going to look almost exactly the same, except that your roller coaster is kind of headed in a different direction. It starts out at a high level, little hill, and then a huge drop on the other side. The reactance is still on the left-hand side, so the energy there is actually higher in this scenario. The product is still on the right-hand side, but the energy in this case is lower. The difference there is the delta H, the heat of the overall reaction. In this case, it would be a negative value. Yeah, and be an exothermic reaction. Activated complex is the top of the roller coaster hill. And then we've got our heats of reaction. The heat of the forward activation energy is there from left to right, and the heat of the reverse activation energy is there from right to left. Okay. And that is all. Okay. Adding a catalyst would make this hill in the middle shorter, which would change the activation energy for both the forward and reverse reactions and make the reaction overall go faster. So thanks for watching. See you in lecture 5.